All right, everyone. Hello and welcome to day 3 of Rustlab. My name is Latara, Talk Manager for this year, and I'll be facilitating these sessions and helping out with the Q&A after the video. One thing I'd like to say before we get started, if you do have any questions to ask, I would like to direct you to the buttons underneath the chat headline. You see two little circles. So next to the room chat, you'll see a question mark icon. Please ask your questions there just to keep things organized. We are about to watch a talk by Pawan Bisht all about a rundown of async await. And so let me go ahead and get started with the bio, and then we'll watch the video for him. So this one is all about, like I said, a rundown of async and await. So Pawan Singh Bisht is a software consultant at Knoldus Software LLP, having a strong experience of more than a year in the technology field. He has been well versed in the core implementation of Rust and Java. He loves to contribute towards the community, and he has also written a book named Best Practices of Rust Programming Language, published on Amazon, to share his experience of Rust programming. And for today, we'll talk about the asynchronous concept of Rust programming by primarily focusing on the internals of asynchronous concept with the practical implementation. And we'll also see how Rust features work internally and what makes a program to run in an asynchronous fashion. As you may know, asynchronous programming lets us run multiple tasks at the same time on a single OS thread. This talk will be about the internal functionality of async await, like what operations are triggered internally so that we can run our programs asynchronously. Important stuff. So enjoy the video. Stay tuned until the end for the live Q&A, and also we'll have a break in the middle. So here we go. Enjoy.
Hello everyone, good morning, good afternoon and good evening to all. I hope you all are doing well. So my name is Pawan Bisht and I am a software consultant at Knoldus Incorporation, focusing on Rust programming language from the last 1.5 years. So today I am presenting a session on rundown of async await. Okay, so as we all know, the async await syntax hits stable Rust as part of 1.39.0 release. So let's understand this stabilized feature in this session and understand how to make our code base asynchronous with zero cost features and with the help of async await feature. Okay, so let's get started now. So this would be our today's agenda, where we'll see what is asynchronous programming. In this section, we'll understand parallelism, concurrency, and asynchronous concept. Then we'll see some alternatives for handling concurrent programming. After that, we'll have a quick introduction on async await. Then we'll have a quick demonstration on async await, and then we'll take a quick break. So, and in the second part, we'll understand some internals and workflow of asynchronous programming. Then we'll compare Rust with Golang. Then we'll see Rust future, and then the internal execution of Rust future. After that, we'll understand the reactor and executor pattern and what's the role of reactor and executor pattern. And at the last, we'll understand the internal execution of Rust future with the help of quick demonstration. Okay, so let's start with our first topic. What is asynchronous programming? So as per the definition, asynchronous programming is a concept which allows multiple things to happen at the same time. Here there are subtopics: the parallel, concurrent and asynchronous. We'll talk more about these topics in further slides. So first, let's understand the asynchronous programming, right? So in a nutshell, asynchronous programming lets us run multiple tasks at the same time on a single OS thread, right? So it means multiple scenarios can be handled at the same time, because when they are waiting for a response, they are just idle, right? So we can let the other task keep working on their computation and whatever they are meant for. So like if we have a blocking call in a program, so we'll not wait for that blocking call. We'll not block our program at that moment. We'll allow our program to continue its further functionality. We are not blocking our program, right? So if we talk about a real life scenario, like, so we can open a large file or query a database, but our program will continue processing each line afterwards, right? If we are query to a database, that might take some time, that could be a blocking call. So we'll not wait for that call, for completion of that particular task. We'll continue our processing each line afterwards. So okay, then let's talk about parallel then. So parallelism is about doing a lot of things at the same time. So here what we can do is we can execute multiple tasks at the same time. We can work them parallelly. So this concept can be achieved only on multi-cores. If we have multi-cores, like as we all have multi-core CPUs, so we can achieve parallelism very easily, right? So what is concurrency then? So concurrency is about dealing with lot of things at the same time. Here we are not doing multiple things at the same time. We are dealing with them, right? So the difference between parallelism and concurrency is the composition of independently executing processes, while parallelism is a simultaneously execution of possibly related computation. So if we talk about more on it, concurrency is basically about dealing with lot of things at once, right? Here we are dealing with lot of things at once, whereas parallelism is about doing lot of things at once. So the point that makes difference between both the statement is the one is for dealing and the other one is for doing. So what is asynchronous then? So asynchrony is used to present the impression of concurrent or parallel tasking. So asynchronous programming just help us to achieve concurrency, right? Generally, but if it's a multi-core, multi-threaded environment, so like asynchronous programming in a multi-threaded environment is a way to achieve parallelism as well. As we already discussed, like parallelism can only be achieved on multi-threaded environment, like on multi-cores, right? Okay then, so moving ahead, let's understand some alternatives for handling concurrent programming. So what we have here is we have two alternatives for handling concurrent programming. The first one is threads provided by the operating system. We call them as OS thread and native threads also. And the second one is green threads, right? So let's understand OS threads first, the native threads. So here what we do is like we just spawn new OS thread for each task, so in OS thread, they talks about the one way of accomplishing concurrent programming is letting the OS take care of everything for us. We do this by simply spawning a new OS thread for each task we want to accomplish and write code like we normally would. Alright, so here the runtime we use to handle concurrency for us is the operating system itself, right? Operating system manages all the things itself. Okay, so let's talk about some advantages. So the pros we have here, they are easy to use, they are simple basically, and here switching between tasks is reasonably fast, and here we get parallelism for free. As we know here, OS spawns new thread for each task, right? So if we talk about the cons here, the drawbacks of OS thread is like OS level threads come with rather large stack. If we have many tasks waiting simultaneously, so we'll run out of memory pretty fast, right? There are a lot of syscalls involved here. This can be pretty costly when the number of tasks are high, right? And the OS has many things to handle. The OS needs to handle many things because it's an operating system. So it might not switch back to our thread as fast as we would wish, right? Because it has a lot of tons of program execution to do. So this is all about the OS thread. So now if we talk about the green threads, the green threads are user level threads rather than kernel level threads, right? So green threads basically they are scheduled by user libraries rather than kernel, and they are managed in user space instead of kernel space, right? As in the case of OS thread, everything is managed by operating system, but here green threads are basically managed in the user space, so instead of kernel space. So it includes context switching. And if we talk about green threads more, like green threads use the same mechanism as an OS. So creating a thread for each stack, each task, setting up a stack, saving the CPU state, and jumping from one task, the thread, to another by doing a context switch. So Rust had green thread once, but they were removed before it hit the 1.0 release. Okay, now let's talk about the pros of green threads. So they are lightweight. Each stack only gets a little memory to start with, so you can have hundred of thousands of green threads running without any issue, right? And here context switching is reasonably fast. So if we talk about the cons here, they are not zero cost abstraction. So Rust had green threads early on, and as we already discussed. So this was one of the reasons they were removed. They are not zero cost. They are non-zero cost. Basically, it's because it was decided that Rust shouldn't have runtime or little as possible, right? But if we have green threads, we need a quite significant runtime to manage those. Okay, so that's the overhead here. So, and green thread maintains a separate stack for each green thread. That's why they were removed, because they are basically non-zero cost. So I think we could consider green thread as a zero cost abstraction, in the sense that we couldn't write an implementation by hand which would perform better. However, the problem was that even if we didn't want to use green threads, we would still have had a runtime in our binary. That's what made them non-zero cost abstraction. We are paying for what we are not using. That's why they are non-zero cost. This is the reason basically they were removed. So here we need to save CPU state on every switch as well, and even they are complicated to implement correctly if we want to support many different platforms. So these are the basically cons of or drawbacks of green threads. So they are quite expensive. So now let's understand the async await by having a quick introduction. So async await is basically a built-in tool of Rust programming for writing asynchronous functions. If you want to write asynchronous code, you can directly use async await feature basically. So if we talk about the async first, so it transforms a block of code into a state machine that implements a trait called future, right? And what is await then? So await is a mechanism to run a future. It asynchronously waits for the future to complete, right? So as it's a built-in tool, and basically async await are a special piece of Rust syntax that make it possible to yield control of current thread rather than blocking. So it basically yield control instead of blocking that particular thread, right? Then allowing other code to make progress while waiting on an operation to complete, right? So we are not making any blocking call here. We just yield control and allowing other code to make progress. Okay, so if we talk about the async, so async basically transforms a block of code into a state machine that implements a trait called future. So here future is a trait, and if you are not familiar with traits, so in a nutshell, traits are interfaces as in Java, right? So there are two ways to use async. The first one is async as a function, and the another one is async blocks. like if you don't want to make a function asynchronous, then you can directly use async blocks inside your normal functions. And each, both like the async function and async block, returns a value that implements the future trait, right? So here, so this is a small snippet here to understand the how to use async in a programming. So this is our so this is a normal function, right? If we ignore the async keyword as of now, so this is our normal function where we are adding. We have a function add which contains variable 1, variable 2, and what we are doing here, we are just adding both the variables and returning the u32, right? So this is a return type. So if we add a async keyword here before the fn keyword, so it makes our program asynchronous, and it basically converts our program converts our function to a asynchronous function. So this is the first way to use async. And the second way is here you can see here we haven't used async keyword before the fn keyword because we don't want to make our function, a whole function, asynchronous. We just want a particular operation inside our function. We just want to make a particular task as an asynchronous, right? So here in that case we can use async block. So as you can see here, I'm using a async block inside a normal function. So it basically returns a value that implements a future trait, right? Now let's talk about the await then. So it asynchronously wait for the future, and when await, the dot await is called on a future, it will attempt to run it to completion. If if future is blocked, it will yield the control of current thread, and when more progress can be made, the future will be picked by the executor and will resume the allowing the dot await to resolve. So we'll understand the internal functionality, this line, the internal functionality of asynchronous, the async dot await, in later slides. Okay, so similar to async, like in async we have two ways to use async in our programs. So similarly to this, we also have two ways to use dot await, right? So the first way to achieve, to use the dot await feature is either we can use dot await inside the async function or inside the async block, right? So these are the two ways. This is inside async function, so this is inside async block. All right, so now let's try to understand both async await feature in our program. So let me show you the quick demo for this. So this is our program. So let me start with the first line. So here I have used the duration of our standard library, and I have used the task of our async std. So async std is basically a async version of our standard library. So, and this statement is commented out, so I'll explain this later on. And after that, I have used a block on function here. So block on is a function of futures. So now as you can see here, we have multiple async functions like function 1, function 2, function 3, function 4, and compute, and then we'll have a main function, right? So let me start with the function 1. So this is an asynchronous function. So what will do is like it will print whenever it will be called. So it will print the statement function 1 started, and then print another statement function 1 goes to sleep for 3 seconds, right? Because I have provided a sleep method here with a duration 3 seconds and provided dot await here. So it will asynchronously wait for this function to complete, right? And at then it will print function 1 ended. Similarly, we have function 2 which will go to sleep for 2 seconds. I have added a sleep method here by providing a duration of 2 and again dot awaited here, right? Similarly to this, we have function 3 that will go to sleep for 1 second only, and we also provided dot await here. So it will, what await will do is like if our function is blocked, so it will yield the control and allow other tasks to proceed. So and at the last we have function 4. So I haven't included any blocking call here. So any sleep method here, so that it will directly print function 4 started, and then after the function 4 started, it will again print a statement like function 4 ended. And what's the role of compute function then? So compute is again a async function. So in the compute function, I have I have to call all the functions, parallelly, at the same time. So I have used a join macro here. So what join macro will do is like it will poll multiple futures simultaneously and returning a tuple of all results once completed. So it will simultaneously wait for all the futures to complete first. So as I have provided 4 function here, function 1, function 2, function 3 and function 4, and after completing all the futures, as they all are asynchronous function, so after completing, the control will go to the next statement where I have printed execution successfully completed. Right, so like in the main function, then I have used the block on method here and just call the compute function. So block on, what will it will do is like, this is the the entry point to execute the feature. It will actually run the future to completion on the current thread. So with the help of block on, we are able to run our future. So let's try to dry run this program. All right, so like in the compute function, I have called function 1, 2, 3, 4, and so when the function 1 will be called, it will print function 1 started and just print the another statement and go to sleep. Then as this function will go to sleep, so we have used dot await here. So what it will do is like it will yield the controller function 1, all right, and pass the control to function 2. Then after function 1 goes out of sleep for 3 seconds, our next statement will be function 2 started, and then function 2 will go to sleep for 2 seconds. Then we again dot awaited here, right? So the control will yield from control function 2 and then pass it to the function 3. Similarly, function 3 prints 2 statements. Again, control will be yield from the function 3 and pass it to the function 4. And then function 4 directly prints both the statement because we haven't used any sleep method here, and so there is no need to await them. Use await anyway. All right. So then function 4 will be started and function 4 ended. So after that, what will be the next statement then? So the function 3 only goes for 3 seconds, so only goes for 1 second, right? So as 1 second completed, again control goes to pass it to the function 3. Then function 3 will print function 3 ended. Similarly, function 2 ended, and at the last, function 1 ended. So let's try to run this program. So okay, let me run using the cargo run. So let's try its building. As you can see here, the execution is still going on. So now, yeah, so it is completed. So we actually dry run the program. So we just discuss that, like the first statement will be function 1 started and function 1 goes to sleep for 3 seconds. Then the control will be yielded by the function 1 and then pass it to the function 2. Similarly, function 2 started, goes to sleep for 2 seconds. Similarly, then as function 2 goes to sleep for 2 seconds, then the control will pass it to the function 3, right? And function 3 would go to sleep for a second, then function 4 started. Because we haven't used any sleep method in the function 4, it will directly print function 4 ended, and as 1 second is completed, then function 3, 2 seconds are completed, function 2, and 3 seconds are completed, function 1. And at the end, we have used a statement in the compute method function like execution completed successfully. So this is the behavior of asynchronous programming, right? So it will not block any call. So let me show you one blocking as well. So if I remove this dot await statement by, we have dot awaited this sleep method here. So if I use only the normal sleep method and just use this one, our sleep method, our standard library. So if I run this program, so it will wait for first function to complete because it's a blocking call here. It blocked the thread. So when first function will be completed, then it will allow others to run. Let me run this program. So as you can see here, it waits for first function to complete. Now first function ended. After that, function 2, function 3, function 4, and then function 4 ended, function 3 ended, and at the last, function 2 ended, and then control will go to the execution successfully completed. So this is how we can achieve the concept. So now let's move to the next slide. Now let's have a quick break. So in the second phase, we'll try to cover the internal functionality and workflows and internal execution of async await.
All right, everyone. As you see, we are taking a small 5-minute break. So go ahead and grab a cup of coffee and see you back here in 5 minutes for the second half of the video. Thanks. Everyone, welcome back. We have finished our 5-minute break. So get ready for the second part of the video. And then at the end, we will have a live Q&A session. I see a lot of great questions in chat. So we'll try to address those live with Pawan Bisht. So thank you so much. Enjoy.
Okay, now let's start with our second phase. So our first topic of our second phase is internals and workflow of asynchronous programming. So if we talk about the diagram first, so at the top level we have syntax and type, then we have runtime and thread pool, and then we have kernel abstractions, and at the last the kernel, right? So if I talk about the kernel first, the kernel already has a concept concurrent parallelism implemented through threads and other concepts, right? However, they are quite expensive, which means there is just a finite amount of resources available, and dealing with this problem on OS level, adds a whole new level of complexity. That's why we need to implement or handle our internal async flow on program level. So to implement this, we need a runtime, right, which can handle our async code and also able to communicate between kernel and our async code, right? And if I talk about the workflow, if like for example, if we mark our method as async, then we can either wait for them to finish, right, or continue with rest of our work, and later on we can check if the method is completed, then we will use the output of that method, otherwise we'll continue the further execution, right? So once we have done with the code, we need a runtime which can take async part of our code and run it. And runtime also need to take processes from the queue and hand it over to the OS, the operating system, because this is the place where actual execution happens at the low level. So when the operating system done with the processing, it will notify the runtime again, and the runtime sets the state inside the async type and hand it back to our program flow, the program workflow, right? So this is a basic of internals and workflow of asynchronous. Now let's talk about Rust versus Go. Like here we try to understand the difference between Rust and Go in terms of syntax, type, and runtime. So if I talk about the syntax, so as we all can see in the picture, Go has a Go routine instead of futures. We'll talk more about future in coming slides. And instead of async await the syntax, we simply write Go methods in Golang. And for runtime, Go has its own Go runtime, but the Rust language team has not included any runtime because they want to be as small as possible. That's why we have to use external crate to provide the runtime, right? Here Tokyo is external crate, and here instead of building our language on top of the runtime, we build our runtime on top of our language, because our language doesn't provide any runtime. So it means if we need to do any async stuff, we can opt into one of the async systems, and if we don't, then we don't pay the cost. That's why Rust itself doesn't come with a runtime. If we will not use any async system, then we'll not pay for this. So as of now, in my viewpoint, the most popular crate for providing runtime is Tokyo, and Tokyo internally uses Mu as its event queue. Okay, now let's talk about the futures first, and then we'll proceed with some internal portion. So as for the definition of this future, futures are representation of some operation which will complete in the future. It is basically a concept for an object which is a proxy for another value that may not be ready yet, right? Future is basically a trait in Rust, and the future trait is at the center of asynchronous programming in Rust. And we can say it is a representation of some operation that will complete in future, as the name already defined itself, right? Representation of some operation that will complete in the future. Okay, and we have mentioned here they are zero cost futures. So why they are zero cost? So Rust futures are purely based on poll model, which makes them zero cost. Like as in other languages, invoking an async function immediately creates a future and schedule it for execution, and awaiting the future isn't necessary for it to execute. But in Rust, invoking an async function does not do any scheduling, and here the main thing we'll notice is that future feels lazy. They won't do anything until we await them inside the async block, or in a nutshell we can say what we don't use we don't pay for. Okay, so after awaiting the future, then the future executor comes into the picture, and we'll talk about executor in coming slides. So to complete the basically pole based mechanism, so the pole based approach have three phases. The first one is pole phase, the second one wait phase, and the last one wake phase. Now let's go to the fourth slide. So this is the Rust future, the basic implementation. So I have added this just to make all clear what is future and what's the actual functionality of future. So if I talk about the snippet I have posted here, so this is a simpler form of Rust future. Let's quickly understand this first. So here we have future trait, which has output as a type, right? And a pole function. The pole function is the major part of the future. It actually starts the flow of asynchronous execution. Like if the future completes, it returns pole ready. The enum we have defined here, the pole enum pole has ready and pending. So if future completes, it returns pole ready, the enum, and if the future is not able to complete or not able to make progress, it returns pole pending and arranges for the wake function, and this function is to be called when the future is ready to make more progress. Alright, so the role of wake function here, the function pointer actually, so is to tell the executor which future are ready to be pulled, and without it the executor would not be able to get the information about which future could make progress, and then executor would have to pull all the futures constantly. Okay, now we have got the understanding of futures by using the simple structure. Now let's talk about the actual or real implementation of future trait. Okay, so this is the actual implementation of future used by Rust programming. So there are two changes that you will notice in this snippet as compared with the previous one. So the first change you will notice here is the self type is no longer mutable self. It is converted to changed to pin and amp reference of mutable self. As this section is related to futures only, so we'll not go deep on pinning side, because we'll try to focus more on the functionality of asynchronous programming. So for now, pinning allow us to create future that are immovable, and immovable objects can store pointers between their field, and it is necessary to enable async await. Okay, so now second change is on wake side, a function pointer. So wake function has changed to the reference of mutable context. Okay, so in simpler form, we used a call to function pointer to tell the future executor that future in question should be pulled. However, since that function is just a function pointer, it cannot store any data about which future called wake, right? So with the help of the context here, we can store the detail of each future who call the wake function, basically who registers for the wake function. So that leads to get detail of the future that needs to be polled. So like at the time of poll, we can directly point to that future that is actually ready to make progress. Alright, so these information are pretty straight from the official documentation. So to know more about it, you can directly refer the official documentation. Okay, now let's talk about the internal execution. So basically we have two options here. The first one would be the thread based, the basically the approach used by operating system, and the second one is event driven architecture. But thread based is limiting because of the limited physical resources we have, right? So event driven is the best in our case. So in this approach, the event driven approach, what we will do is like it will register incoming future request and saves a pointer to the async function handler. Then it triggers an event in the kernel to basically execute the operations. So once the IO operation is done, we call the pointer again and execute the async method with the result of the kernel. So in the diagram you can see at the top we have async await as syntax and future as async type. So please and then we have the runtime our runtime, that is Tokyo, that includes a reactor and executor pattern. So here you can see here the reactor is used to notify the executor. Remember the wait phase we have discussed in the poll based approach. So this is same. So Tokyo internally then uses mu, like it uses epoll, kq, like async kernel method. So we'll not go with these methods. We'll try to understand the functionality of asynchronous programming with a basic flow. So this is user land, and in the kernel we have kernel IO task, and in the CPU we have multi-threading, hyper-threading, and multi-processing, and so on. Alright, so now let's try to understand the reactor executor pattern used by Tokyo here. As you can see here, the reactor executor pattern. So an executor is essentially a scheduler. It is responsible for actually executing the future that got spawned as task onto it. However, if a future can't make progress, it needs to ensure that future is getting notified again. So that's the job of reactor, right? So this happens via waker function. We registered for a wake function at the wake phase. So this piece actually noticing that the task can make progress again, and calling the waker is the reactor. So this is the job of reactor, to notify the executor that future is ready to poll again. Alright, basically reactor notifies if data is coming over the network or operation are in progress, and executor takes the data and execute the async function, future with it. It basically apply the it comes under the poll method, where we are actually executing the future, we are extracting the data from the future, right? So okay, now let's understand the whole functionality with a quick demonstration. Okay, let me show you the implementation then. So this is a program where we try to achieve the asynchronous concept with the help of the future. Like we already discussed about the syntax of future. We have a thread future with the type output, and we have a poll function. So this is the actual the main reason to to complete the asynchronous concept. So we have a enum then, and which contains ready or pending. So if our future is complete, then we will send the poll ready, otherwise poll pending if the future will not able to make progress. So let's start with the starting first. So here I have used refcell as an import statement. So refcell is because refcell is basically a mutable memory location which dynamically checked borrow rules, right? So I have provided a thread local macro here just to declare a new thread local storage key of type, right? So we have used notify here and the refcell type of bool, and just initializes with the default value. So we have provided default to true, right? Then we have a structure called context, which has an attribute waker, right? And the type of this waker is waker, and waker itself again a structure. If we talk about the implementation of waker, here we have a wake function. Remember the wait phase where we register for a future. We register a wake function for a future, like whenever future is ready to make progress, this wake function will call and we can poll that future. And in the implementation of context, so it includes two functions, from waker and waker. So the purpose of from waker is to provide the context of a future, and the purpose of waker is to provide the waker. Right. Okay then. So moving ahead, so I have defined, I actually used the structure here, future progress, and inside this I have used an attribute process of progress of U32, and just mark this structure with a derived attribute default. So this default will initialize the value of this structure, that value for attributes with a default value. So as I have used U32 here, so it will initialize the value with a 0. So like if we run the program, then we'll start our progress with 0%, right? Okay then we have implemented a future trait for this structure, and then inside this we have an output of I32. We just use the signed integer value, and then we just define the poll method here. We provide the definition of poll method, so it will return poll self output. So output is this one for this in this case, and you can say here, you can see here I have provided a statement like using the println macro, checking whether the poll is ready or not. So just use a pattern matching here. So if self.progress, like our progress is 100%, just assume like it's in the percent. So if our progress is 100%, then we'll return poll ready, and otherwise the control will go to the default case, and in the default case we just increment our progress by 20% and register for a wake function. Just call the wake function here and return poll pending. So let me tell you the so I'll explain the functionality of wake function while we try to dry run this program. Then I'll show you the the actual the usage of wake function. Okay, then we have a run method here. So I'll show you the functionality of run as well at the time when we try to dry run this program. So then in the main function, so we have used we have just created instantiated our structure future progress with the default function. So it will initialize the value with the default ones, and we have we just use the variable my future progress, and then we are executing our future using our run method and just providing a statement. Okay, now let's try to understand the behavior of run, the functionality of run. So run method here, what will do is like it accepts a future as an argument and return a future output. Here f is a future. Okay, so as we discussed, like f is a future here. So then we just use a notify with the thread local storage key here. We provide a with. So it basically what will this function will do is like this the attribute will do is like it loops until we have provided a loop here. So it loops until it get notified that future is ready to be polled again, right? If our future is ready to be polled again, then our control will come outside this function by returning a value, so that our future, our executor can execute our future. Okay then, so inside this we are used a looping here. So inside this we just use is ready. We take the value is ready here from here. So we just immutably borrow the wrapped value and checked whether it is true or not. So but initially we have provided the value to true at the very first statement. You can see here here. So now the control will go inside our if function. Now we mutably borrows the wrapped value and updated the value. Let's assume like now like our future is ready to make progress. So okay, then we come inside the if block, and we are trying to consume that future. We are trying to extract that future, or you can say that to execute that future. So as of now we just updated the value to false. Okay, like we have executed our future, so just make it false. Then after that we are getting the context from the method using the context from waker. We already discussed like from waker provides context. Here it returns the self type. It means it provide a context here. So we get the context, and by passing the waker method here, the waker structure you can say, which implements which we have included here the waker one. So okay then, sorry, this one, the structure, where is this? Yeah, this one. Okay then, we have provided a waker. So now we get the context. Now we just trying to validate the future is ready to poll or not, right? Okay, so we are using if-let condition here, like future poll ready value with like we just calling the poll method here. So what poll method will do, like poll method needs a context. So we already received the context from the from waker function. So we provided a context to poll function. Okay, let's go to the poll then. So this is the implementation of poll. Okay, now we got the context of our future. Then we are checking is our progress is 100%, but initially the progress is 0 because the value is initialized with 0, right? So the control will go inside this. Okay, then now we are incrementing our percent with 20% and just calling the wake function. So let's go to the wake function then. So what it will do is, like, it will update the value, the our local storage key to again true, because we have updated the value to false here inside our when we are trying to execute a future, right? So again we have we just, because we are calling the wake function, it means it will wake again. So that's why we are making it to true again, right? So after making it true, it will return poll pending, like our future is not ready to poll, right? Or make progress. So again the loop will execute it. So again we have a true because inside the wake function we just updated the value to true. Then we again make it false, and similarly we get the context again. We try to validate the poll, and at the second phase now up poll function will get a value 20. So similarly 20, 40, 60, 80, and after 100 this method will return poll ready. So whenever it return poll ready, so this condition will satisfy. If let poll ready equals to poll ready, yes. So then we come into this if block, and it will print finally our future is completed and will return our value that is 100% now, right? So then we'll print like 100% future is completed and with the value returned by our run method. So let's try to run this program. So if I run this is our output, right? So we just provided a statement check whether ready to poll or not. We just provided this inside our poll function. So initially, at this stage we have a value 0, progress value of progress is 0, then 20, 40, 60, 80 and 100, and when the value turns into 100, it will return future poll ready. Then we got the output from our run method, and we just provided finally our future is completed and return the value. Then the control will go to this print statement, and we return 100% future is completed. So this is how we can achieve the synchronous concept using the small this code, you can say this code base. Okay, so I have used the reference of this code from the Google itself, but I just try to manipulate the program just to just to explain it more better way. So this is all about this demo and the session as well. So if you have any query, please feel free to ask. And these are the links, so you can contact me directly using Gmail, LinkedIn and Twitter. And I have also added a GitHub link as well. So thank you very much.
All right, everyone, welcome back. We are ready to go live with Pawan Bisht to answer your questions. There are so many of them. We might not have enough time to answer all questions, so I'll try to prioritize the ones that don't seem to have answered themselves in some way or another. So let's bring Pawan Bisht live for you all. Hi there, welcome back. Thank you so much for all of your contribution to Rustlab. Before we start with the questions, do you have anything you want to say about your participation in Rustlab?
Yeah, so
Yeah.
in Rustlab, so this is the first time I'm presenting in Rustlab. So I was very excited to present my session here. So that's why I, include. I just submit a proposal for async of it, as this is the new feature for Rust. Although it is a stabilized feature since 1.39.0. So I just want to share my experience to all. So that's why I submitted a proposal for Slack. Thank you.
Wonderful. Thank you so much. All right. We'll try to get to all of the questions. We've got so many of them. So let me start with this first one here, which is, could you elaborate a bit more about user space in context of green threads?
Yeah, so green threads are basically comes under the user space because they are not managed by kernel. So as far as I know, green threads are implemented at the application rather than kernel, and this is usually done when the OS does not provide any thread API. So it doesn't work the way we need. So so basically to manage the scheduler in our own way, so we need to use the green threads, and that's why basically green threads are comes under the application level or the user space, so that we can manage. And the advantage here for user space is we are not depending on the OS, you can say the operating system libraries or kernel. So here we can schedule the mechanism of our green threads by our own. So this is the basic understanding I have of
Great.
green threads.
Okay, thank you for that. The next question was a little confusing for me, but I'll try to read it in the best way possible. Arif says, in slide 12, the example of async function versus sync block, you said you don't want to make the whole function
Yeah.
async.
Yeah,
So
so got
go
it,
ahead.
got it.
Go
Yeah,
ahead.
got it. So first of all, so there is a misleading statement. So I apologize for that. So I just want to explain it, like if we don't want to use the async keyword. So there are two ways to use async. Either we can use async keyword before our for fn keyword, so that we can make our function asynchronous, and the another way is using the async block inside the async function. So yes, the whole function is asynchronous still. So because we are the this makes a program asynchronous by using the async block inside our async function. So I agree with the point. So this there is a misleading statement. So the point here is just to explain it the another way to use async block. So the whole function is still asynchronous. So that's misleading. Yeah.
Okay. Thanks for clarifying. We have kind of a follow-up question by Jonathan. He says one of the big gotchas for async in C is async over sync, or using async functions in a sync context. And how does Rust manage async when you're not running it in an async function?
So I'm a little bit confused with this question.
Yeah, let me re-paste it here in the chat, just in the main chat there.
Yeah, so I have the question here. So the question at the last line is, how does Rust manages async when you're not running in an async function? Like, so if you're not using our async function, then our code is not asynchronous. So it is synchronous. So if we have any blocking also, our thread will block at that time. So I don't know in the context of C sharp. Actually, I'm not getting the question properly here. So the only point here is, like, if we are not using async or we are not implementing future for our functions in Rust, so that means this is not a asynchronous call or asynchronous function.
Okay, hopefully that clarified things a little bit more. Thank you. Next question comes from Arif, and he says, I wonder if waiting is a better term than blocking, because if all things block, then it's only the things that block due to the waiting that concern us, right?
Yeah, so actually, yeah, I have used the sleep method there. Just to show. Actually, I tried to mimic the scenario where like if we query a database, so there might be this could be that could be a blocking call, right? So I just try to mimic that scenario, like if our program contains any blocking call. So our program will not block, our thread will not block, it will continue afterwards. So so I just try to mimic that scenario using the sleep method by waiting it. So this is just to explain it more better way. But so this is basically just to explain it the difference between our async flow and with the blocking flow.
Okay,
So this
thank
is
you.
just for explanation.
Great, great. All right, we've got 3 questions left. Hopefully this one hasn't been addressed already, and that is, what is the difference between using async await syntax versus implementing future while writing asynchronous program in Rust?
So this is the very actually it's a good question here. So as far as I know, there might be some internal reasons to have async await in our Rust programming over futures. But the if we talk about in general way, so async awaits lets our implementation very easy if we compare to our actual future implementation. So if we, for example, let's say example, if we are trying to implement a synchronous function in Rust, and we are returning a future from our function. So in the implementation part, we have to provide the by providing the future implementation explicitly, we have to use the OK and error methods future. Like if that's a positive response, so we need to wrap our final response in the future OK, and if there is some error, so we need to wrap it on the error block. So async await simplifies the implementation. So this is the, you can say, the basic reason behind this. But there might be some there must be some internal functionality or internal reasons to have async await. So as far as I know, like as of now, I can only provide you the simple reason here. So this basically makes our implementation very easy as compared to the actual feature implementation.
All right, great, thank you. We have 2 questions left. Hopefully we can get to them. We're over time. The next one is, are there tools to visualize the workflow dependencies of async functions?
Are there tools to visualize workflow dependencies? Actually, I didn't the question properly, so can we get the more clarity on the question?
Okay, yeah. While you get clarification, maybe Janek, you can. Okay. Yeah, people seem to say they haven't seen a tool like that before for workflow dependency. Okay, maybe if he wants to clarify, in the meantime, I'll ask our final question here, which is, can the user influence the scheduling, dynamic, static?
Can the user influence the... So actually, I need some more clarity on this as well.
Okay.
In which context we are talking about.
Okay. So maybe... So Janik says, like in Python Dask, for the first question about the tools to visualize the workflow.
Yeah, so like in Python, I don't have understanding of Python, so I haven't worked
All right.
Python.
All right, so let's see, I think that's it. If the user creates his own runtime, then sure, he can influence the operation of async.
If the user creates his runtime, then sure, he can influence the operation. Yeah, if like as of now, user is not like, as far as I know, like as per my experience, I'm not directly talking about if user creates his runtime. So we just use the runtime to run asynchronous, to run our futures. So basically, runtime helps us to interact with the OS and our basic functionality. So I'm not sure with this question. I don't have any concrete answer for this.
Okay, well, thank you, Whitney, for that time. You guys, we are out of time, so I'm going to go ahead and greet you all. Thank you so much, Pawan, for being here. And hopefully next edition of Rustlab will have it live, and we would love to have you there as well. So thank you so much. All right, you have a great rest of your day. Thank you.
Thank you so much. Thanks, everyone, for
Thank
joining
you, guys. All right. So I just want to remind you all that if you liked this talk, you can rate it on the agenda page of the Rustlab site. We'll be waiting for you for the next talk of the day, starting in about 5 minutes, which is the state of WASI support in Rust and Web Assembly Toolchain by Michael Yuren. So we'll see you in about 5 minutes in that room. Talk to you then. Thanks.